Today's lecture is on Wye and Delta transformations, also known as T-pi transformations. The objective of the lecture is to describe the equations that relate the resistances in a Wye and Delta resistor network, and describe what a bridge circuit is in terms of Wye and Delta subcircuits. Wye and Delta networks are three-terminal arrangements of components. Shown here are three resistors in each arrangement. However, capacitors and inductors may also be used. These circuits may also be drawn as four-terminal arrangements of components. The T network is shown above, which is equivalent to the Y network, and the pi network is shown below, which is equivalent to the Delta network. As you can see, to convert the three-terminal arrangement to a four-terminal arrangement, two of the terminals are connected at one node. The node happens to be a distributed node in the case of the pi network. On this slide, I have listed the relationship between RA, RB, and RC, the resistors in the Delta network, to R1, R2, and R3, the resistors in the Y network. I'm certainly not going to read through each equation, and they are listed in your textbook. Given the analysis techniques that you have learned thus far, you should be able to derive these equations. However, I won't make you do that either. If all of the resistors in a Y network are equal, then RA equals RB equals RC equals 3 times the resistance value used in the Y network when you assemble the equivalent delta function. And if the resistors in the delta function RA equals RB equals RC equals R prime, then all of the resistors in the equivalent Y network will be equal to R prime divided by 3. Y and Delta networks are used in a number of applications, in particular power systems, most notably in the distribution of three-phase power. They are also used when distributing power to the stators and windings in motors and generators. Y windings provide better torque at low RPM, while Delta windings provide better torque at high RPM. Another network of components that's used frequently are bridge networks, shown to the right on this slide. The measurement of the voltage between two of the nodes in the bridge, VCD, is used in sensing applications as well as full-wave rectifying circuits. If RA equals RB equals RC equals RD, then the voltage drop between the two nodes, VCD, is equal to 0 volts. In sensing circuits, the resistance of one resistor, and we usually choose RD, is proportional to some parameter, temperature, light, pressure, whatever. Then VCD becomes a function of that particular parameter. There are a number of different ways to analyze a bridge circuit. You can view this bridge circuit as back-to-back Y networks, or as two Delta networks where RC1 equals RC2 equals an infinite ohm resistor. Alternatively, a bridge circuit can be constructed from one Delta and one Y network, again where RC is equal to an infinite ohm resistor. I have redrawn the original circuit such that all resistors are perpendicular. If RA equals RB equals RC equals some resistor value R, and RD happens to be the same resistor value minus a delta R that's a function of the parameter that you're trying to sense, and you go through the math to determine what VCD happens to be, you find that VCD is equal to 1 divided by the quantity 1 minus delta R over R times the total voltage drop from one end of the bridge network to the other, VT. In summary, though we haven't gone through the math, there is a conversion between the resistances used in a Y and Delta resistor network. We have also seen that bridge circuits can be considered to be a combination of YY, Delta Delta, or Delta Y circuits. Using the equations associated with voltage division, the voltage across a bridge can be shown to be related to the change in the resistance of one resistor if the resistances of all three other resistors is held constant. This is the basis of sensor circuits using bridge circuits.